everyone, welcome back. We have a special guest joining us today. Say hi, Rory. In this video, we're going to talk about inference for a single mean. So what do we do with a numerical variable? We'll start by introducing yet another probability distribution, the t-distribution. We'll then talk a little bit about how we can find confidence intervals for a population mean using the t-distribution, followed by how to do the t-test. So let's start with the sampling distribution of the mean. We've already learned that assuming our sample size is large enough and the population is relatively symmetric, the sample mean follows an approximately normal distribution. Now, if we know the population standard deviation sigma, well then we can say that the sample mean follows this normal distribution and we can do calculations with it fairly simply. However, this is usually a difficult assumption. When we do, for example, a hypothesis test about a population mean, we're making an assumption about what mu should be. But we are not making the same assumption about our standard deviation. And it turns out that this is usually a piece of information that is missing. So in the past, what we've done is use the sample standard deviation, S, to estimate the unknown population standard deviation, sigma. However, it turns out that this brings some additional variability into the picture. There are now two sources of error from our sample. Our sample could poorly estimate the sample mean x bar. It could also provide a poor estimation of the sample standard deviation, S. So we've got two chances to go wrong. This is a frustrating thing when we've got two chances to go wrong, but luckily we do have a solution available. The solution here is to calculate a new test statistic that we'll call the t-statistic. You've actually seen this already in the previous video. So this quantity t, which is equal to the sample mean x bar, minus the population mean mu that we're hypothesizing, divided by s over the square root of n, follows a new distribution called the t-distribution, or the T-Rex distribution. In our graph, what you're seeing here is the standard normal distribution plotted in red and several different choices for t-distributions in blue. Now, right away you see a difference. There are several different choices for the t-distribution, which is kind of a downside of this. However, notice what happens as the blue line gets darker. So as the blue line gets darker, we're increasing a parameter associated with the t-distribution, something called degrees of freedom. Look what's happening. This t-distribution, as the degrees of freedom are increasing, becomes very similar to the normal distribution. So they're not that far off in reality. So this t-distribution is used then to help us account for the extra variability that comes to us from estimating the standard error using the sample standard deviation. There are some properties of the t-distribution. The first thing that we've already noticed is that the t-distribution is another example of a symmetric bell-shaped curve. The t-distribution also looks a lot like a normal distribution. The t-distribution is a fatter distribution, meaning that it's more spread out on the ends. In practice, what this means is that t-values that are farther from zero are more likely to occur with a t-distribution than they are with a normal distribution. So the t-distribution is more spread out, in other words. The t-distribution is also centered at zero, so that's another similarity in common with the normal. Unlike the normal distribution, which has a mean and a standard deviation, so two parameters, the t-distribution only has one parameter, something called degrees of freedom. Finally, the larger our sample size gets, the closer this t-distribution is going to end up getting to the standard normal distribution. That has to do with how we define the degrees of freedom. So for better long-run accuracy, when we're working with a numerical variable, anytime we have to make an estimate for the standard deviation, so use that sample standard deviation, we'll use the t-distribution in place of the normal distribution. There is a downside here. The t-distribution changes depending on the sample size or depending on the degrees of freedom. That means it's a lot harder to work with values from a t-distribution by hand. In fact, this is how one would have had to work with values from a t-distribution by hand. So we would need to find the appropriate degrees of freedom and then look through a table for the appropriate t, matching those degrees of freedom. Not fun. So now what we'll do instead is use R to help us find that t very quickly. So let's start with how we would apply this new t-distribution to find a confidence interval for a mean. So based on a sample, we can be whatever our confidence level is confident that the true population mean is between the following. We'll take the sample mean, add and subtract some value from the t-distribution, we'll call that t star, times the standard error of the sample mean. This is very similar to the formula we used in the previous video. However, we're now replacing that 1.96, which we previously got from the normal distribution, with some value from a t-distribution. So we can use the qt command in R to find what this t star is directly, or for some problems you may simply be given a t star to use. So for example, let's find t star for a sample with 10 observations, so n equals 10, and a 90% confidence level. Now it turns out that when we're working with a single sample, the t-distribution that we need to use is the one with degrees of freedom n minus 1. So for our first problem here, notice the degrees of freedom, or the df argument, is our sample size 10 minus 1. What we would like to do is find the value from the t-distribution that gives us the middle 90% probability, just like the value of 1.96 from a normal gave us the middle 95% probability. So here, in order to get that, we will take 1 minus 0.10, so we're looking at the probability on the ends here. If there is 90% probability in the middle, there is 5% probability on the left, 5% probability on the right. So our cumulative probability is then 5 plus 90. This will become 95. So it's a little bit complex, a little algebraic at first to figure out what these QT probabilities need to be. It turns out that the value of t star that we would use in this particular situation to get a 90% confidence interval is 1.83. For a 99% confidence interval with 15 observations, our probability is 99 plus 0.005 because that's what's left over on the ends. Our degrees of freedom are 15 minus 1 or 14. So we would use for our t star value in that confidence interval 2.98. So this is the major disadvantage of working with the t-distribution versus the normal, is that there are a lot more steps to figure out how to calculate this confidence interval by hand. Luckily, we won't have to do that too much longer. So let's take a look at an example just so we can get a feel for how this confidence interval actually works. So outside of currently living cells, it turns out that the most common place on Earth where you can find DNA is actually on the ocean floor. Organisms living in the ocean die, they drop down to the ocean floor and deteriorate, leaving behind trace DNA. DNA then has over time become a vital component in sea life nutrition. Organisms that live on the ocean floor eat the leftover DNA. So a random sample of ocean floor specimens from 116 locations around the world gave the following summary statistics in terms of DNA concentration. So we have the average DNA concentration for these 116 locations, that's X bar. We also have the sample standard deviation denoted by S. We'd like to calculate and interpret a 95% confidence interval for the mean ocean DNA concentration by hand. In order to do this, we also need our value from the t-distribution. So degrees of freedom are the sample size minus 1, that's where df equals 115 comes from. A 95% confidence interval gives us 0.975 probability up to the right. So the value that we'll use for this 95% confidence interval is 1.98. So plugging everything into our confidence interval formula, we get the sample mean 0.2781 plus or minus 1.98 times our sample standard deviation 0.1803 divided by the square root of 116. So I get a confidence interval here that goes from about 0.245 to about 0.311. Now when I do these calculations, I tend not to round until the very end. If you round at a step in between, your answers may be slightly different from the ones that you're seeing in the videos. So let's interpret this confidence interval. What is this telling us? Well, based on our data, we're 95% confident that the population mean DNA concentration on the ocean floor is somewhere between 0.2449 and 0.3113. So changing to the t-distribution hasn't affected how we interpret these confidence intervals at all. The only thing that's really been affected or impacted is just what we multiply the standard error by. So let's take a look at another example. We have data from a study in the Journal of the American Medical Association, or JAMA, that included 3 groups with 25 subjects in each. The control group consists of healthy individuals with no history of brain trauma who were comparable to the other groups in age and educational attainment. Our second group then consists of NCAA Division I college football players with no history of concussion. Our third group consists of, again, Division I college football players with a history of concussion. What we're looking at here is data on the brain hippocampus volume taken from high-resolution MRI. Is there a difference in the size of the hippocampus depending on whether or not there's been a history of concussion? So to visualize this data, I've created what's called a density plot. Think of this density plot like a smoothed out histogram. I've drawn a smooth curve over what a histogram of this data might look like. We can see that the red group on the very right, this is the control group, so no football, no concussion. They tended to have the highest hippocampus volume. The football players with no concussions had slightly lower hippocampus volume. However, those with concussions in green had by far the lowest hippocampus volume. So we'd like to compare these 3 groups. The table here, produced using the favestats function, summarizes the total hippocampus volume for the control group. What we'd like to do is calculate a 95% confidence interval for the mean total hippocampus volume for all non-football players. So in our control group, we'll find the mean, which is 7,602.6. Standard deviation, this was the most variable group of 1,074.02. Here is the value that we need from the t-distribution. So at home, take a moment, see if you can calculate this confidence interval using the formulas that were provided. All right, if you've paused the video, time has passed. If you haven't, well, time didn't pass. Anyway, let's take a look at the answer. So we'll get 7,602.6 plus or minus our value from the t-distribution times the standard error. So our 95% confidence interval for the mean hippocampus volume for non-football players is 7,159.3 to 8,045.9. I'll leave this example for you all to do at home. Calculate the 95% confidence interval for the mean total hippocampus volume for all football players without concussion. So now this is row 3, football, no concussion. The answer that you should get if you're checking your work is 6,137.3 to 6,781.1. Okay, so now that we've covered how to do a confidence interval using this t-distribution, it's just a slight tweak on our previous formula. Let's jump into our hypothesis test. This procedure that we're about to work through is probably one of the most famous or most widely used statistical procedures. This is an example of the t-test. So our first step is to write the null and alternative hypothesis. Our null hypothesis represents an assumption about the population parameter, and we're assuming that it's equal to some value. So we write for a population mean that mu is equal to some value, say mu0. Our alternative hypothesis represents an alternative claim based on the research question. We can use either a less than hypothesis, a greater than hypothesis, or a not equal to hypothesis. Step 2 is to compute the test statistic. So based on our observed data, we come up with some test statistic as a measure of how far the data truly is from the assumed population mean. So we calculate a t-statistic in this case, x bar minus mu0 divided by s over the square root of n. Our next step is to determine the p-value. So based on this test statistic, we calculate the probability of observing data as or more extreme as our sample, assuming the null hypothesis is true. We will let R do this in the background for us, but we should know that this p-value is calculated based on the t-distribution. We'll use a command in R Studio called t.test to help us out. And then finally, we'll make a conclusion about the original research question. So if the p-value is small enough, we'll reject our null hypothesis and say that there is strong evidence to support the alternative. If the p-value is not sufficiently small, we will fail to reject the null hypothesis and state that there may not be evidence to reject it. In other words, the null is plausible. Now, before we look at some examples, I do want to talk a little bit about a characteristic that the t-test and the t-distribution often gets attributed. It's often said that this is what's called a robust statistical procedure, and this turns out to be pretty true. What this means, this quality of robustness, means that the result is not often hindered by departures from this assumption. The variable is normally distributed in the population. Technically speaking, that is an assumption that we make when we're doing the t-distribution. Some textbooks really hammer this assumption in, others are hand-wavy. I tend to fall in the middle. As long as our sample size is large enough and our data isn't severely skewed, so isn't strongly skewed left or skewed right, the t-distribution tends to work fairly well. I do want to mention at this point that when the sample size is small, there are other procedures that we can use. So let's take a look at an example. Is there sufficient evidence to show that the population mean total hippocampus volume for football players with a history of concussions is less than 6,000 microliters? Our null hypothesis is that the population mean mu is exactly equal to 6,000 microliters, or the population mean hippocampus volume is exactly equal to this value. Our alternative hypothesis is that the population mean mu is less than 6,000. The population mean hippocampus volume is less than 6,000 microliters. We will use the function t.test in order to do this test for us. I want to walk through what this code is doing before we look at the output. So the first thing that I've done is actually create a new data set in R called FB concuss. In this first line, what I'm doing is taking the original data set called football brain. This had all three groups. And I'm using the pipe operation to pass that into a function called filter. And what I'm doing here is I'm filtering out all of the groups that are exactly equal to football concussion, FB concuss. So now I have a smaller data set that just has football players with a concussion. So in the t.test function, here is how we write this. Our first argument is the variable that we care about, and we indicate that this is the variable we're interested in with a tilde or with a squiggle. So tilde hippocampus says, hey, let's look at the hippocampus variable. we're going to, in our null hypothesis, assume that the mean mu is 6,000, so that is what comes next. Our alternative hypothesis had a less than sign, so we'll write less in quotes for our alternative. This can be either single quotes or double quotes as long as you're consistent. I tend to favor single quotes so that I don't have to hit the shift button to get the double quotes. And then the data is the football concussion or FB concuss data set. So this output goes ahead and calculates the t statistic for us. So our t, if we use that formula, should be negative 2.24. This means that our sample mean is about 2.4 standard errors below what we would expect if the null hypothesis is true. Our p-value is 0.01, so it's pretty small. Based on that small p-value, less than a 2% chance of seeing a sample like this if the null hypothesis is true, we should reject our null hypothesis. If we reject it, we will then conclude that yes, there is strong evidence that football players with a history of concussion have a mean hippocampus volume less than 6,000. Now, let's take a look at slightly tweaking this formula. So instead of providing a mu argument for my hypothesis, an alternative argument for my alternative hypothesis, what if I do this? What if I write conf.level equal 0.95? We should ignore the t, we should ignore the p-value that's provided because we're not actually doing a hypothesis test when we write the code in this way. But look at what we do get. We get a confidence interval. So we can calculate the confidence interval for our data directly, also using this t.test function. We just have to be conscious to replace the hypotheses with the confidence level. Now, you may be wondering why this t is 48 here. Here's why. If you don't write this mu argument, R by default will assume that your null hypothesis is that the mean is equal to 0. So our sample mean is 48 standard errors away from 0. Now, for a lot of reasons, a hippocampus volume of 0 microliters is not clinically relevant, not of interest, not possible. Plus, since we're looking for the confidence interval anyway, we don't particularly care that R is assuming 0 here. But that's just an interesting quirk of the output to look for. Let's take a look at one more example. So we have radioactive cesium tissue that is produced by nuclear reactors. A study was done to examine this cesium tissue concentration of a random sample of bluefin tuna captured off the coast of California 4 months following the Fukushima nuclear meltdown in 2011. The idea being that this nuclear waste product was released into the ocean when the Fukushima nuclear plant melted down, then consumed by tuna and other fish in the ocean. The data here is measured in becquerel per kilogram of dry tissue. So we have the mean of about 10.26. Standard deviation is 2.89. Our sample size is fairly small. We have a sample of 15 tuna. Historically, radioactive cesium concentrations in bluefin tuna have been below 2 becquerel per kilogram on average. Here is what we would like to know. Is there strong enough evidence? Is there, quote, statistically significant evidence that the radioactive cesium concentration in bluefin tuna has increased? Now, before we do this hypothesis test, let's use a little bit about what we know from the data to make a prediction. Here's a histogram of the cesium concentration in these 15 tuna. The lowest value that we observed in our sample was a little over 4. So the lowest value was twice as much as the historical concentration. So before even going into this formal hypothesis test, we should have some feelings or some intuition that we're probably going to reject the hypothesis. So is there significant evidence to show that the radioactive cesium concentration in bluefin tuna has increased? We'll start by writing our hypotheses. So our null hypothesis is that the mean mu is equal to 2. Our alternative is that the mean has increased, it's greater than 2. Unfortunately, our code has disappeared. At home, try to think about how you would write the code to do this test. We get a result for our t-statistic of 11, so that means we are 11 standard errors higher than what we should expect to see. Our p-value is 1.5 times 10 to the negative 8th, so that is 0.70 followed by a 1. There is very compelling evidence here to reject the null hypothesis and conclude that the population mean cesium concentration has increased. Now finally, if we would like to do something like use a 95% confidence interval to estimate the mean radioactive cesium concentration in all bluefin tuna, we would use that t.test function. Think about how you might write this at home. Here is what the output looks like. Unfortunately, there's a typo here, so this should be 99% confident down below. Based on the data, we are 99% confident that the population mean radioactive cesium concentration in bluefin tuna is between 8.4 and 12.48 becquerel per kilogram, so significantly higher than pre-Fukushima levels. In the next video, we will start to look at how we can go beyond just a single sample by looking at paired data. We'll see you then.